Hello and welcome to my presentation about our study that is entitled TasKar, a research and education tool for calculation and representation of binary classification performance instruments. My name is Gürol Canbek. This study focuses on a fundamental topic in binary classification, performance evaluation. Before going into production, a classifier's performance is obtained as a confusion matrix and calculated and reported in terms of different performance instruments. This study specifically focuses on the representation and calculation of both the matrix and instruments. We cover an ultimate set of instruments viewed from 4 dimensions of a confusion matrix, namely the number of true positives, false positives, true negatives, and false negatives. A total of 52 performance instruments are covered in this study. Taking parametric and variant and recently proposed instruments, the number covered becomes 65. The contributions of the study as follows: proposing a textual formatting schema to represent different performance instruments, providing free novel graphics to visualize performance instruments together, and presenting a new dashboard, TasKar, provided online for calculating and presenting the binary classification performance with a total of 65 instruments. TasKar is the abbreviation of Tasnif Karnesi or classification report in Turkish. The tool is provided online for the researchers in my GitHub repository, which is also called TasKar. As an introduction to the domain or the topic, as you know, binary or two-class classification separates given inputs or examples into two opposite classes, dichotomies, which are called generally positive and negative. As we now live in a pandemic world, diagnosing COVID-19 and its emerging variants specifically from blood tests, X-ray images, or CT scans or any other modalities via machine learning algorithms will definitely be a vital solution for the whole humanity. There are many attempts in the literature. However, ensuring the assessment and comparison of classifiers' performance truly, precisely, and objectively becomes a critical requirement to achieve such robust and high-performance classifiers. As we covered in this study, despite the various metrics proposed in the literature, researchers and practitioners use or report just a few well-known metrics, such as accuracy, F1, or TPR, which is also known as sensitivity or recall. This practice might be an indication of lack of understanding in general about those other alternative performance instruments. Now I would like to summarize the contributions of this study. The first contribution is proposing 3D representation and textual formatting for performance measures. This could be significant for understanding and conceptualizations of performance instruments. How should we color the classifier's input and outputs might be a good start for this study. As you know, a binary classifier takes some inputs as in classes or ground truth and makes some predictions by yielding some outcomes. So it accepts positive and negative classes and makes some predictions by yielding outcome positive or negative. In this study, we suggest that we should use clean colors for the inputs, but the outcomes should be colored in foggy or dirty colors because there is an uncertainty in the outcomes. It might be right or it might be wrong. Following this design decision, we choose clean red and green colors for positive and negative noun labels or classes respectively. Likewise, the counterparts of the outcomes are a little foggy and dirty colors, indicating uncertainty. Here you can see some examples of binary classes represented in class colors. Because the target or positive classes are usually more concerned in classification studies, for example malware, spam, illness, or any other rather abnormal phenomena, they are represented in red, whereas green-like colors imply secondary or normal concerns, for example benign software, a regular email, or healthy. After coloring input and output classes, the second research question in establishing a textual formatting schema is how we can color the four elements of a confusion matrix. We proposed a three-dimensional representation of performance evaluation. On the ground, we have positive and negative non-labeled inputs in clean red and green colors. But we evaluate the performance by looking into the outcomes and comparing the ground truth. An observer can see the four elements from above as follows. When a classifier produces an outcome positive, there can be two possibilities. The given input was also positive, that yields true positives, or the input was negative, causing false positives. Notice the color variance at the top level. Likewise, when the outcomes are negative, it could be a true negative where the input was negative, the classifier makes correct prediction, and it could be false negative, incorrect prediction. Based on the proposed 3D representation, we define a complete textual formatting schema for the confusion matrix and 7 base measures derived from the matrix. As we said, we put prediction above ground truth. Then we added 4 elements of the confusion matrix. As you can see, the overlaps of outcomes and ground truth exhibit a slight color variance in all elements. Per each element, we choose a text color from prediction and a background color from the ground truth. After adding the other 3 totals, diagonal and off-diagonal, and 4 totals, into the initial 2 ground truth and 2 outcome measures, we finally get these coloring schema for 11 base measures. Here you can see the complete palette definition of the text and background colors of those base measures. Before going into the second contribution, I would like to summarize the limited number of related works on visualization of confusion matrix or performance metrics. The first representation is from MATLAB, an engineering software package. A plot confusion command simply displays the confusion matrix and some of the performance metrics in a tabular format. The second approach employs a visual representation for confusion matrix and 4 base measures via relative sized semi-ovals. Here you can see the ground truth, and via a line bisecting these ovals, it shows the relative sized outcomes. Each section yields also the relative sizes of the confusion matrix. Here you can see a similar approach from R, another engineering software package. The graphics output of fourfold plot command shows the performance measures with circular sections relatively. In this example, different performance evaluation cases are depicted in Venn diagrams. Here you can see a more elaborate approach to depict confusion matrix, ground truth prediction classes, as well as well-known performance metrics such as accuracy. Considering the limited suggestions in the literature and software packages, we propose three novel graphics to visualize performance instruments in a well-defined and easy-to-understand manner. The graphics proposed are explained based on the classification results you see. The first graphic shows the prediction performance of a classifier. The outer circle shows the positive predictive value and false discovery rate, and the inner one shows a negative predictive value and false omission rate. You can compare the positive versus negative predictive values. The concentric circles make it easy to distinguish the relative performances for each metric. In a similar approach, the second graphics show the ground truth performance metrics. You can compare the ground truth versus prediction performances by looking into both graphics. While two proposed graphics depict the performance from a clear point of view, the class sizes are excluded in particular. To include the sizes, we propose a single graphic showing true ground truth metrics in x-axis and true outcome metrics in y-axis. You can easily compare ground truth versus prediction performances per classes. Moreover, the red and green circles depict and display the size of positive and negative classes respectively. In this manner, the class imbalance effect is clearly distinguished by the users. Remarkably, the different aspects of performance can be neatly represented and sensed via a single picture. The third and last contribution of this study is a research and education tool for classification performance evaluation. I have developed and provided a tool named TasKar as a calculator and dashboard for a total of 65 instruments. The tool also provides the three proposed graphics. I try to arrange the layout of TasKar having such a large number of instruments as compact as possible. At the core, it is the confusion matrix or 4 Bayes measures. You just need to enter these 4 values to see the corresponding instrument values and graphics. Then the first level measures come surrounding the matrix. Next, prediction or row Bayes metrics are at the left, and ground truth or column Bayes metrics are at the right. All the other derived instruments are located accordingly. Finally, the three proposed graphics are attached at the bottom. You can download the latest version of TasKar as an OpenOffice calculator in my GitHub repository. You just need to install a free and open source Office software. Classification performance evaluation in terms of a large number of instrument alternatives is conceptually and practically problematic. This study provides well-defined, tangible solutions to enhance our understanding of the instruments and assist the individuals to see and interpret the complete results. It is expected that the research community and industry practitioners embrace the proposed schema to meet a common performance evaluation and reporting method and find TasKar useful by making their decisions faster, accurate, and more objective in a wider perspective. specifically free from confirmation and publication biases. Thanks for listening.